Hello, I am Kyle Scott, and this is my Constant Velocity Lab presentation. For this lab, I rolled a marker across the whiteboard. I chose a marker and a whiteboard because both are very smooth, so there would not be much friction between the two bodies. When I performed the experiment, the marker moved in the negative x direction with almost constant velocity. The constant velocity of the marker can be explained using Newton's first and second laws. Newton's first law states that an object either at rest or in motion will continue to stay at rest or move with the same motion if no outside forces acted on the object. Newton's second law states that the net force acting on a system is equal to the system's mass times the acceleration of the system. Based on Newton's laws, the lack of any significant friction means that the marker would move with constant velocity. Despite the fact that gravity and the normal force from the whiteboard both act on the marker, the two forces cancel each other out in this situation because they have the same magnitude but act in opposite directions. Therefore, there is no net force acting on the marker, and it will have constant velocity. I demonstrated the constant velocity of the marker in this tracker video. As you can see, the marker moves in a straight line in the negative x direction with almost constant velocity. I could have aligned the axes such that the marker was rolling in the positive x or negative or positive y directions. However, the only thing this would have changed is the direction of the velocity vector. The magnitude of the velocity vector would have stayed the same. While the marker appears to move with constant velocity, I was not able to achieve perfect constant velocity because the cap had bumps on it. I had to keep the cap on to make the marker go in a straight line. This little bit of friction caused by the bumps is seen in the graph. But for the most part, the graph is a straight line, indicating constant velocity. I then took some of the data from Tracker and used it to make a computational model in Python. I used the initial position 0.156 meters and the velocity negative 0.592 meters per second. I chose this velocity because it best modeled the data out of the given velocities. Here is my code and computational model. As we can see, the model shows the marker starting in the positive x direction, moving with negative velocity in the negative x direction. From here, I combined the data from Tracker and the data from Python into a Google Doc and created a graph. Here we can see that for the most part, the computational model lines up with the experimental data. Due to the bumps on the cap, we see that some of the points are slightly above or slightly below the line, but the variance is not very large. Overall, the computational model models the experimental data well. As shown in the graph, the marker rolling across the whiteboard in this lab demonstrates how a system maintains constant velocity when no net forces act on the system.